Earth is our home, and we like to think of it as pretty well understood. But really, we're still learning a lot about it. From plate tectonics and continents to the time the Mediterranean Sea disappeared, here are 6 mysteries about our planet we're still trying to solve. First, there's the question of how and when plate tectonics started. The Earth's crust and very tip-top of the mantle are divided into floating tectonic plates, which are constantly moving, pushing against, and slipping under each other. And from this process, we get phenomena like earthquakes, volcanoes, and moving continents. Understanding plate tectonics is fundamental to understanding Earth. In fact, you could even say it's the bedrock of geology. But even after more than 50 years, nobody can pin down how and when this whole deal started. Part of the reason is because there's very little physical evidence left from the early Earth. And what is left is kind of up for interpretation. So 2 scientists looking at the same sample might come to 2 completely different conclusions. One way we've investigated this, though, is by using mineral samples like ophiolites to try to nail down a start date for this cycle. These are fragments of ocean crust preserved in continental crust, and they could only have formed if plates were already colliding or sliding across each other. So if we find them in rocks of a certain age, it could be evidence plate tectonics had started by then. Some of the oldest ophiolites we found are 3.8 billion years old, which would suggest that plate tectonics was active in some form early on. But other suggested dates range from almost immediately in the Earth's life cycle, over 4 billion years ago, to less than 1 billion years ago. So that's quite a range. Meanwhile, scientists are also looking into this by creating and testing computer models. A 2015 study, for instance, used models to investigate mantle plumes, immense upwellings of magma from deep within the Earth. And it found that 1 or more ancient plumes would have had enough force to crack the early Earth's crust and kickstart the tectonic cycle, which would have been amazing to watch from a spaceship. Not on Earth. Figuring out this conundrum is important because it wouldn't just help us understand life on our planet, but in the universe too. Because plate tectonics hasn't just shaped how our planet looks. It's also done things like keep the atmosphere stable by adding and removing carbon dioxide. That helps keep our planet from tipping into either freezing or boiling. And because of this, some scientists think that these plates might be necessary for life to develop and thrive on other planets as well. No matter how things kicked off, plate tectonics started slowly rearranging the face of the Earth. And that leads us to our second mystery. Some 250 to 350 million years ago, the continents got squished together into one giant landmass called Pangaea. It was what scientists called a supercontinent. But it wasn't the Earth's first, and it won't be the last. And like plate tectonics, more generally, this repeat supercontinent cycle has had a profound effect on our planet's crust, atmosphere, oceans, and life. The breakup of Pangaea might have triggered a global change in climate, for example, as fresh tectonic rifts released CO2 into the atmosphere. But explaining why this cycle exists and what drives it is trickier. Again, a lot of the physical evidence is up for interpretation. And also, it's possible that no 2 supercontinents formed for exactly the same reason. Case in point, one of these possible forces scientists are looking at to explain supercontinent formation is called extroversion. And it's nothing like the personality trait. In it, you start with a supercontinent. Then a new ocean forms in the middle and pushes the other plates away. Eventually, the ocean grows so much that the plates circle around the globe and end up shoved into one area. But as a 2008 paper pointed out, while extroversion alone might explain some supercontinents, it struggles to explain every episode of supercontinent formation, including Pangaea. Instead, that might have been caused by extroversion's opposite, introversion. In that case, the cycle starts the same, with a new ocean opening up. But then the process stops and reverses, drawing the other plates back together again like a giant drain. One test that scientists can use to try to figure out what drove certain episodes is by testing the age of marine deposits from tectonic plate collision zones. This can tell you whether they came from old oceanic crust or young oceanic crust, which would be characteristic of extroversion and introversion respectively. Another thing that might be the result of plate tectonics is the Messinian salinity crisis. About 6 million years ago, the Mediterranean got cut off from the ocean as something closed the Strait of Gibraltar. The Mediterranean naturally loses more water to evaporation than it gets from rivers, so without new water from the strait, it began to dry up. And while exactly how much it dried up is controversial, we know it left kilometer-thick salt deposits behind and had major local effects on climate and fauna. But why did that closure happen? Just looking at the rock itself is tricky, because it's hard to pinpoint the age of the layers. There aren't many fossils, for example, which normally serve as signposts. So we've had to turn to other methods, like looking at volcanic rocks. In 2003, scientists comparing rocks in the area from different time periods noticed a shift in the ratio of elements found in rocks, which they think indicates a change in the mantle. They propose that around the time of the crisis, a tectonic plate shifted, allowing hot mantle material to push up, lifting the land around the Strait of Gibraltar out of the sea and closing off the gateway. Eventually, though, the crisis passed and the Mediterranean started filling up again. Although exactly how that happened is another head-scratcher. And of course, this whole idea is just a hypothesis, so as always, more research is needed. Volcanoes regularly bring magma to the surface, reshaping and creating new land. Most of the time, this is only important in small areas or for short periods of time. Like sometimes a powerful eruption might destroy an island or temporarily affect the world climate. But more massive eruptions, known as flood basalts, can occur. They can cover more than 1 million square kilometers with magma thousands of meters thick. And some of them, like the Siberian and Deccan traps, have been implicated in mass extinctions. So naturally, we want to know why they happened. One conventionally cited cause might be mantle plumes, those giant upwellings of material from near the Earth's core. Another might be delamination, where part of the lithosphere, that's the crust and upper mantle, falls away from the tectonic plate it was attached to. But we don't have definite answers about how or why these things might happen. After all, they're events that happen deep within the Earth millions of years ago. But there are ways scientists can try to decipher why flood basalts occurred. In 2006, for instance, a paper studied the age and makeup of xenoliths, which are rocks stuck inside other igneous rocks. They were looking at xenoliths that would have formed in the mantle just underneath the crust. And they were looking in a layer of rock that would have been deposited soon after a flood basalt event. What they were working off of is that if delamination was actually the cause of the flood, the loss of that chunk of lithosphere should also mean the loss of those xenoliths sitting just inside or below it. So the scientists could look at the age of any xenolith they do find, and if there was delamination, there should be no mantle xenoliths older than that event. Looking at these rocks, it does appear that delamination happened at some point under China, for instance, but not for other events, like ones in South Africa. So the science continues. The Earth's axis of rotation naturally drifts and wobbles over time. In the 20th century, for instance, it seems to have moved about 10 centimeters per year, in part because of a rebound effect from the last ice age. We can map this polar wander via satellite, and understanding it is important for climate modeling. But the Earth's wobble might not always happen at such a steady and stately pace. In fact, there's evidence there have been major shifts. Around 174 to 157 million years ago, for example, East Asia went through a drastic change from wet seasonal to extremely arid. And this was devastating for animals living there. There have been some explanations for this before, but in 2019, a paper suggested this shift was due to polar wander. If that's the case, it would mean the Earth essentially twisted, sending the area that's now China 2,800 kilometers south. Like today's minor wobbles, these major twists would be tied to some kind of redistribution of Earth's mass, from things like impacts or glaciers. The excess mass gets flung, so to speak, toward the equator along with the Earth's crust and mantle. It's just what physics says will happen to a spinning sphere if it becomes unbalanced. That said, it's really hard to pin down exactly where and when these shifts happen. One technique we can use is paleomagnetism. When magma cools, it takes on different magnetic signatures based on where it is in the Earth's magnetic field. So if we see a series of rocks undergoing a quick, drastic change in their signatures, it might be a sign the area they were in moved very quickly. That said, the rocks can be an imperfect record, since later bumps and squeezes can change that signature, which means, again, it's hard to say anything definitive. Alternatively, for more recent episodes, it's been suggested that we can use volcanic hotspots like the one underneath Hawaii. Because the crust is only floating on top of the mantle, it's technically possible that the crust shifted while the mantle stayed about the same. And because those hotspots are features in the mantle rather than the crust, we can use them to track how the crust has moved. Finally, one of the very well-established facts in geology is that the Earth's core is very hot. But the question is, how hot? Those specifics would help illuminate a ton about how the Earth works, like how the magnetic field is generated, how the planet formed, and even how we could predict earthquakes. Figuring out that temperature is tricky, though, because we can't just drill down there with thermometers. So we have to get creative. One thing scientists are doing is studying how iron acts under high pressures and temperatures in diamond anvil cell experiments. In these experiments, scientists measure what happens when small amounts of a sample are heated and squished between two diamond-tipped pushers. The idea is to put iron in one of these anvils, then squeeze and heat it until it's the same density as the Earth's core. A density we already know thanks to other measurements. When you reach that right density, you can check what the iron's temperature is, and that should give us the temperature of the core. Using this method, a 2013 experiment revised the estimate for the melting temperature of iron at the inner core boundary from about 4,800 degrees Celsius to about 5,900 degrees, which is about as hot as the surface of the sun. It doesn't look like there's been any super huge shakeups in that number since then. So maybe this is a mystery we're putting to rest. That said, that's the thing about mysteries. It only takes one new study to open up the door again. Earth is our home, but it's a home built by forces and processes, many of which are invisible, long gone, or mind-bogglingly complex. Often, all three. So our planet is not just set dressing. It itself is one of the great mysteries of science, too. Thanks for watching this episode of SciShow. If you liked learning about geology, you'll probably really enjoy our special 3-part series about the geology of Olympic National Park in Washington. We actually went to Washington to film it, which was a whole new thing for us, and we learned a lot as a result. You can watch the first episode after this.